What would have been total? I would have to pay
Okay, so I had a question about this problem I saw, I think it was on Monday. Okay, we're at this point where we get P dt equals 1800. Is that clear?
Yeah.
So the question is, if P dt is 1800, we're going to figure out what time.
My question is, how do we determine that P
Sure, yeah.
equal to 1800?
Oh, this comes from.
Yeah, that's mine.
Sure, I can fill it out. So this equation.
That's all they usually buy. Well, I do that, I know, but if you divide,
So
you don't get 45.
you don't. Okay, so
You don't get
you basically do this right-hand side and you multiply these two and then get it down. And that you're left with P dt now. Is this 1800? We can just check quickly if the calculations.
It's 40 times 1.5 squared. Divided by 2 is 45. Divided by 0.2. That equals 272.72. So that's what I kept getting.
So this thing is 45. The right-hand side is 45, right?
Yes.
And then we got to divide 45 by 0.55.
Times 0.3.
0.3 comes to 272. Huh. Okay, so looks like I made an error here, but let me check with this.
So this is what I did. So you get P equals 45, but N equals 0.55P. So plug this in here.
Okay, looks like I did. Let's so the solution in the book agrees with this 45. Apparently, there's some problem with this. Let me figure that out. What's wrong? What I'm trying to do here is I'm trying to use from 2. So let's go. So I use this equation. Is n equals point. So this is right, 0.55p.
Yeah, that's all. Everything's right all the way up until the 1800 bar.
I think I'm forgetting a momentum. Is that right?
You might be.
Yeah, so I see the mistake. This is dimensionally inconsistent. So if you look at the right hand side, that's I times omega, which is actually equal to a moment. Moment is m0 dt, but this is not a moment. This is just a force.
Yeah.
I'm missing the moment arm here, and the moment arm is. So the moment arm comes because of mu kn, and I should have it in the free body diagram, mu kn. So that's acting at a distance of. So this is a moment about O. So I need to consider this distance, 0.15. So I'm missing 0.15, and so that 0.15 should show up here. So I'm missing a 0.15 here, and see if you can get 1800 now with 0.15. So 45 divided by 0.33.
So when we're doing our moment, we did our moments about A, so it should be used to say N times 0.15.
Okay, 1818 here. If I put all these values, I get 1818. It's very close to, so time will change slightly. 1818 minus 500.
Oh, yeah.
So 4.63. Yeah, so there was an error with my moment. That was we have an equation for the moment. That moment is this. The moment is force times the distance from the point about which you're taking the moment, which in this case is O. So mu kn is the force of friction. You need to multiply it with the momentum, which was missing in my original equation. Okay, any other questions?
Yeah.
Okay, so let's move on. More problems.
Oh, yeah, it's 500 plus 500, 200.
So the 30 megagram, which is 30 times 10 raised to 6. G grams is equal to 30.23 kilograms. So 30,000 freight car and a 15 mg. So 15 mg is 15,000 kilograms. Freight car B are moving towards each other with the velocities shown. Okay, 20 and 10 kilometers per hour as shown. Determine the maximum compression of the spring mounted on car A. This is a spring. We have to find the maximum compression. Okay, so there's a when two blocks collide, and in this case we're going to assume that they actually stick together and they move as a single unit, which is not given here. So if you're not given this, you either assume this or assume that the freight cars move as a single unit after collision. Okay. In fact, if you're not given that, and if you're not given E, then if you're given E, then you got to use coefficient of restitution to figure out what the velocities are after collision. In this case, not given, so I'm just going to make an assumption that they're going to stick and they're going to move as a single unit. Okay. Now, normally when you have a collision of two blocks, energy is not conserved. Okay. But in this case, the second assumption we're going to make is that when the two freight cars collide, and because there's a spring in between, the energy which is coming from the collision is stored inside the spring. Okay. So we also assume that collision energy, so there is no energy loss because the spring stores the energy. Okay, normally we would give you those things. We will not. I mean, the first one we should definitely give you. The second one is something which you got to figure out yourself. Okay, so again, I'm going to follow this recipe. First, is it a kinematics problem? Well, you're given the mass, and so this is not a kinematics because you're given the mass. Are you told to find the velocity when the object moves a certain distance? In this case, yes. In this case, basically the spring which is compressed. Spring has you got to find the maximum compression of the spring. So when you have you're given the velocities like you have in this problem, and you're told to find the compression, which is the displacement, you got to think of conservation of energy or work energy. Now in this case, number 2, there are only conservative forces because the only force in the collision is spring force. And since there is no energy loss, which is an assumption I've made, that all the energy from the collision is stored in the spring, I can use principle of conservation of energy. Which states that T1 plus V1 equals T2 plus V2. Okay, so let's write down T1. In T1 is the initial kinetic energy, so mass A is moving with the velocity A squared plus half mb vb square. Okay, we'll assume that the spring is not compressed or stretched initially, so the energy stored due to the spring is 0. Okay, since the two blocks or two freight cars move as a single unit, the kinetic energy after collision is going to be ma plus mb times v square, where v is the common velocity. Okay, plus the energy stored in the spring, so half k s square, or we can write it as x square because this is motion in the x direction. Okay, so we know the initial velocity of both the cars, we know the mass, we are also given the spring constant, so we know k. So what we do not know is v and x. So we have two unknowns and one equation, and we cannot solve for two unknowns with one equation, so we got to generate one more equation. So the question is, how can you get the second equation for either v or x or v and x? Conservation of momentum would be the. So no matter what, the momentum is always conserved in a collision. Okay, if there are no external forces. So we assume that when these two freight cars collide, the forces during the collision are internal to the system, and so if you look at the complete system as a whole, then the momentum is conserved. So principle of conservation of momentum, which states that summation mvi before collision equals summation mv after collision. So we can write these expressions. So ma va plus mb VB equals, since both the freight cars move as a single unit, MA plus MB equals V, where V is the same as the common velocity. So in this case, the only unknown in this problem is V. VB, MB, everything is known. Okay, so solve for V using 1, and this is just a matter of plugging the values. V comes out to be 2.778 meters per second, and then solve for X using 2, because we know V now, so we can solve for X. It's 0.48 meters.
There's, yeah.
Okay, any questions? Okay, so here's a problem where you got to use two principles. These are principle of conservation of energy, which is chapter 14, and then you got to use conservation of momentum, which is chapter the next one, 15. Okay, and so really, if you look at everything, it's asking the question, what are the concepts? So we started off with this. We got one equation, and we saw that that equation by itself cannot solve the problem. So we had two unknowns, and then we asked ourselves, what else can we apply? And that's how we came to conservation of momentum. So think of it. The way I like to think of a problem is, if you start thinking of the problem, what are you asked, and then what principle to apply, then you get somewhere. In this case, we actually got to the point where we identified the conservation of energy from this, and then we were stuck because we couldn't use that equation by itself, and so we had to search for something else, and that's where you have to sort of think beyond this sheet, right? And so it is really hard for me to tell you how to go about getting the second equation, but that's something you got to think. When you have a collision, the conservation of momentum is the way to go. Okay, so I would say more practice. So this can help you to some extent. For this a problem like this, it is really hard for me to tell you conservation of momentum is the way to go. I can get you to the point where you think of conservation, but the second equation has to come from practicing more problems. Okay, so I think this makes this particular exam hard, where you got to be not only able to identify what concept, but sometimes there are more than one concept from multiple chapters which need to go in solving problems. Okay. But any questions on the previous problem? No. Okay. Next question. The 10-pound bar is pinned at its center O and connected to a torsional spring with a spring constant of 5 lb feet per radians, so that the torque developed is 5 theta. Okay, so this 5 theta comes from the spring, okay, where theta is in radians. If the bar is released from rest when it is vertical at theta equals 90, determine its angular velocity when theta equals 0. So initially the bar is this way, and finally it is this way. And the direction of rotation actually depends on how exactly the spring is connected. So in this case, well, we can. It's really hard for me to tell you if this is a compression spring or tension spring. So if it's going to turn clockwise or counterclockwise, we can just assume either one. And actually, the answer will not depend on that, because you'll see that I just assume it counterclockwise because that's easiest for me. And then you'll see that it actually doesn't matter in this problem, because you'll get the signs will actually come out to be will work for you and will give you the right answer. So again, let's go through. Let me write down the unknowns before I try to solve this. We got to find angular speed when theta is 0 degrees. If the bar released from rest, so it's released from 0 speed when theta is 90 degrees. Okay, that's given. Okay, so if we go through this, first of all, it's not a problem in kinematics, number one, because you're given the mass and you're also given capital M, which is a moment. It's not, well, is it? Number two, are you told to find velocity when the object moves a certain distance? In this case, it's not velocity, but it's angular velocity when the bar moves a certain angle in radians, right? And so that would also qualify for 2. So this is a problem involving, well, concepts in 2 should be applied. Are there only conservative forces? Now, it's not given here, but no gravity. Actually, gravity wouldn't have mattered in this problem, because the middle portion of the bar is pinned, and so even if gravity had acted, it wouldn't have created an external torque. Now, if I had moved it slightly so that the point O is not the center, it was offset, then yes, gravity would have affected under gravitational field. So no gravity or gravity does not affect the problem. The solution will be independent of whether there is gravity or not. So there's a spring and there is no gravity. Okay. So one way to do this is clearly a conservation of energy. But hold on, my bad. It doesn't quite say that it's a spring constant. It says the torque developed is M. Okay, so it gives you an external torque. M is external torque. So when you're given an external torque, I'm actually hesitant on using conservation of energy, because I do not know if that torque is a conservative torque, creating conservative is a conservative force or not. So I'm more inclined to skip 2A, instead use 2B, which does not make any assumption about the nature of forces. So let's use principle of work energy. Principle of work and I'm doing that because M or an external okay, so conservation of principle of work energy states that T1 plus U12 equals T2. Okay. Initial kinetic energy is 0 because angular speed is 0. Let me write the right hand side, that's much easier. Half I omega square. Okay. Why did I write half I omega square? It's because the rod has only rotational kinetic energy. So there is no energy associated with translation. So normally I would write half mv square plus half I omega square, but since there's no linear speed v, that part is 0. So only rotational energy. Okay, so we're left with the work done, and that's work done is due to m d theta. Theta goes from 0 to pi divided by 2. So
It's 0 squared because there's no velocity initially, is that what you're saying?
the velocity is 0. Initially is 0. Well, this should be swapped, right? The initial angle is pi divided by 2. The final angle is 0. Should be swapped because initially it's at 90 degrees. Oh no, my bad. 0 and that was right. Initially it's 0. Final is pi divided by 2. M is counterclockwise, so it's positive, and theta d theta is is it initial 90? Oh, my bad. So I wrote it. Yeah, my bad. I should say. So it's not right. Should be 0 to pi by 2 to 0. Okay, so actually the solution here makes an assumption that the moment is negative, but there's nothing here which is indicative of that. Why is that true?
Because it spins clockwise.
Because it spins clockwise.
Well, because you're taking theta from the positive x-axis. You can see.
Yeah, so this is positive theta. And
it starts like this, and then so it has to rotate like this.
Yeah, it starts like this way, it goes this way. So the moment is that way. So
It would be negative.
Yeah, so the moment is this way. I mean, I would do a better job of defining the moment. So the moment is negative because it's clockwise. Yeah, if they had just put that, then that would have helped for the moment. So it's negative because it's clockwise, and so we got to do is pi by 2 to 0 minus 5 theta d theta equals half. The inertia of a rod about its center of mass is 1 divided by 12 mass times length squared, so minus 5 theta squared divided by 2. Upper limit is 0, lower limit is pi by 2. The mass is 10 divided by 32.2 because that's in lbs. The length is 2. Omega square is unknown. And so if you solve this, you get 10.9. Okay, if you've looked at I can post the solution from the book. The book solves this using Newton's laws. Okay, but you don't need to use Newton's laws. You can use principle of work energy to solve this. Okay, any questions? Okay, so a problem like this, you would actually be given the inertia of a rod, and so that's a hint that it's not a problem in a particle, but it's a problem involving a rigid body. Okay, let's move on. The 10 lb collar B is at rest, so its speed is 0, and it is in the position shown. The spring is unstretched, so the spring here has no force when it's vertical. If another 1 pound collar A strikes it so that B slides 4 feet, so B slides 4 feet, determine the velocity of A just after impact and the average force exerted between A and B during impact if the impact occurs in 0.002 seconds. The coefficient of restitution is 0.5. So this is what's going on. A has a velocity VA. I'm going to put VA1 for the velocity before collision, and VB is the initial velocity of the collar before collision, so that's going to be 0 because it's at rest. After collision, VA is going to have a new velocity, it's called VA2. VB is going to have a new velocity, let's call it VB2. It's not equal to 0. So P4 collision, after collision, I'm just going to put the right side to be the positive direction, so I can just assume that, and then the math will basically give me positive or negative. And so eventually, because B has a non-zero velocity to the right, VB2, it's going to start moving to the right. However, the spring is going to stop it from going and hitting the wall on the right. Okay, the spring is going to slow it down, and so eventually, if this is the initial position, this is going to be the final position. 3, 4, this is B. So you're told that it stops at 4 feet. Let's see, what are you asked to find? You're asked to find velocity of A just after impact. So this is the unknown. VA2 is the unknown. Okay, we can solve for the impact force a little later, but VA2 is unknown. That's what I'm trying to first solve for. Okay, so this is a problem which is slightly different from the rest, because you got to think of what happens sequentially. So A hits B, and so how do you figure out what is the velocity of A and B after collisions? That's something you got to think about. Then B goes from its current position, which is vertically down, all the way to the right, and comes to stop at 4 feet. So that's another phenomenon, right? It's working against gravity. So there are two events. One is the collision at A and B, and then motion of B till it comes to stop on the right side. Okay, now you're given where it comes to stop, and you got to basically backtrack. Given the information that moves 4 feet, can you solve for VB2? So this is given. I'll try to solve for VB2 first. Okay, so going backwards, and once we know VB2, I think we can solve VA2, because we know what happens in a collision. In a collision, there's coefficient of restitution equation, and then there is conservation of linear momentum. We could apply both those things. So my goal is to go backwards for this particular problem.
Is it not easier to go like forward?
You could, yes, you could go. Okay, if you want to go forward, that's fine too. You just end up with a lot of unknowns, and you want to do forward, let's do it forward.
Or if you do restitution, then your VB final becomes your VB initial, and you can use work energy
Yes, so you could do it forward. So if you do it in the reverse, then you'll see that you'll actually solve for many unknowns. And if you go it in the forward direction, you'll have a lot of unknowns in the equations, and only towards the end is when you'll be able to solve. So if you think forward is much easier, let's do it.
The other way, whatever is easy, I don't know.
The book solves it reverse, let's solve it forward. So it is what I take in post the solution. Okay, let's solve it in the forward direction. That's fine. If you think that's hard to do it reverse, let's do it forward. Okay, so forward direction. So we got to first analyze collision. The key is to analyze collision and analyze motion under the spring. Okay, so first of all, when it's a collision, there's conservation of momentum. So M A V A before collision plus M P V B before collision equals M A V A after collision plus M B V B after collision. Now in this equation, what we do know is velocity of B is 0 because B is at rest. VA2 is unknown, VB2 is unknown, VA1 is given. It's not given, sorry, my bad. VA is not given, right? Yeah, it's not given. So there are too many unknowns. There are 3 unknowns. So 3 unknowns, we got to generate more equations. That's 1. The second equation we'll generate is restitution equation, which is straightforward. Minus E equals velocity of separation divided by velocity of approach. So velocity of separation is VA2 minus VB2 divided by VA1 minus VB1. In this equation, what we do know is E. We do know VB1, which is 0. And so we have 1, 2, 3 unknowns too. So we have 3 unknowns in the first equation, 3 unknowns in the second equation. Okay, the second piece is analyze motion of B only. This is when it's moving under the influence of the spring. Okay, so B has a speed, let's call it VB2. It's going to be stretched by the spring is going to get stretched, and it's going to apply a force which is going to retard the motion of B. In this case, we know the velocity of B when it starts. We know the velocity of B when it stops, because that's the maximum extension of the spring, and so we sort of know velocity as a function of distance, right? We know 4 feet is the distance traveled. So if its velocity is a function of distance, then it is number 2. Number 2 says if there are only conservative forces, use conservation of energy. In this case, the only force is due to spring, and so we can use conservation of energy. If that rod had friction, then you cannot use conservation. You'll have to use work energy. So no friction. Nothing has been said about friction, but you can make the assumption if nothing is given. So analysis of motion of B would be, we would use conservation of, there's a third one, energy. Okay, so that states that T1 plus V1 equals T2 plus V2. The initial kinetic energy is half mb VB2 square plus you're told that the spring is initially unstretched, so the spring energy is 0, equals final kinetic energy of the block B to the right, it's 0, plus V2, which is the energy stored in the spring, and that's going to be K times the length of the spring in the stretched state, which is this length. That's 5 clearly, because 4, 3 and Pythagoras theorem will give us 5, minus the unstretched length. The unstretched length is the length when the force is 0, which is 3. Okay, now in this particular expression K is, I believe, given. It's 20. So K is given. MB is given. So VB is the unknown, and we can solve for VB. So the first thing to do is to solve for VB. So VB comes out to be 16.05 feet per second. Then I would take this VB2 and put in this equation and also in this equation. Okay, so now if you look at equation 1, what's that?
How is VB2 16.5
You have to put
1/2 10 times VB2
10 divided by 20. So once you put VB2 in equation 1, okay, we know this now. So we have two unknowns, VA1 and VA2. Similarly, when we put VB2 in this expression here, we know this, we'll have two unknowns, VA2 and VA1. So equations 1 and 2 are two equations in two unknowns. Originally there were three unknowns, but now we've found one unknown, and so two equations, two unknowns, you can solve for velocities. So last step is two unknowns, and you can solve for the two unknowns. Velocity of A, which is asked, comes out to be 118 feet per second. But you can solve for both VA1 as well as VA2. Okay, and it comes out to be to the right. And then there's one more thing in the question which is asking for the force. Hold on, let me write both things. VA1 is 108. VA1 is 118 feet per second. VA2, which can also be solved for, it comes out to be negative 42.8 feet per second. So it's negative means it's going in the left direction, not to the right. Okay. However, we're asked to find VA1. The last part, and I'll let you go after this, is to find the force. Let's see. Average force exerted between A and B during impact. The impact occurs in 0.002 seconds. So what's going on there is because the two blocks interact, there's a force, an impulse force. Okay, and we got to find the value of the impulse force. That impulse force is actually given by m times, it could be MA VA2 minus VA1. That's one way to find it. You could also find it as MB VB2 minus VB1. Okay, I'm forgetting the time, delta t.
Is that on the formula sheet?
That's probably not on the formula sheet. It should be F divided by delta t. Yeah, so delta t is up. F impact. I think this should be negative. Yeah. This comes out to be 2492.
So we should memorize that equation.
Yes, that's the impulse equation, right? Impulse is F divided by delta t, and that's equal to mv. It's actually Actually, that's in the formula sheet. Let me show it to you. It's actually in the formula sheet, I think. It's in the formula sheet this way. If you look at LMB, it says that f dot dt equals f dot dt. Yeah, my bad. This should be delta dt. Yeah, so LMB says mv2 minus mv1 or something like that. Just check that equation. I think that equation is there. That's the one I used. It shouldn't be delta t.
So that equation earlier, that was wrong. It's wrong.
Yeah, it's wrong. So it should be divided by delta t.
What's delta t?
Delta t is the time.
So it's 0.002.
Yeah, 002. Delta t. Okay, I'll see you on Monday.